you know, trying to make the weight work. Okay, so the other question people ask those people who are serious planetary scientists, they say, you know, down on Mars it's really cold, and if you go into a cave on the moon, it's really, really cold. Of course, Mars has a little bit of atmosphere to distribute some of the heat and average things out. But if you're down in the cave out of the sunlight on Mars, how do you keep your robots from freezing? I was going to use the other word, but I can't use the laughing. He knows what I was going to say. So, and we've developed the concept of a metabolic system, because what happens is these fuel cells are giving off heat. When you combine oxygen and hydrogen, what you get is water, electricity, and heat. And that heat, in fact, can be regulated to keep our little robots nice and toasty, warm inside. So we've done that. So that's, and it's called metabolic because it works the way you and I work. In other words, our internal energy processes give off some heat. And actually, it gives off enough heat that what you have to do is regulate the activity of the ball from getting it overheated. So if you ask it to hop too much and too fast, much like some of us who might think about jogging, you'd really get hot and sweaty. So you don't want to get your little robots too hot. What about sensors and electronics? Well, it's interesting what's happening with sensors and electronics. There's a lot of research going on in sensors and electronics to make it very, very small. One of the major motivations for this is homeland defense. The government's putting a lot of money into making sensors that are very small so that they can put little observers everywhere in the world to see what's happening, distributed all over New York City to see if somebody's putting out some bad chemicals or whatever. But there's major programs in putting sensors on what they say on chips, basically, as well as the need for microcomputers. We all want our laptops to get smaller. We all want our palms to get smaller. We want telephones to get smaller. So you start to do things. So like a pressure sensor, you can now buy a pressure sensor which is that big. You can't even see it. Okay, hardly see it. Okay, compared to a dime. You can buy a Fuji CCD camera that is there, which is not much larger than a match head. Okay. So there's a lot of sensors around that you can buy, and a lot of electronics that one can buy. You can buy that is a accelerometer and an IMU, inertial measurement unit, that's got effective solid-state gyros on it and accelerometers and things like that. You can buy GPS receivers that are down in the order of a few grams. So there's been a lot of work, and we believe that within this time frame that there'll be no problem getting all the electronics we need, which are very low power. This is a miniaturized mass spectrometer that's coming out of Draper Laboratories that's up near MIT, Cambridge. So mass spectrometer gives you the ability to measure the chemical basis of what you're looking around for. So lots of laboratory on a chip are being developed right now, and we will propose to exploit that. Simple task communications, that's a computer, okay? And what's really funny is that those of us who are probably a little bit older remember when we had when we would use floppy drives that would carry a 280 byte, and then things got better, and we got the zip drives, and they got better, and they're still this big, and then we got things, and now I got a thumb drive with 3 gigs on it. That's like my thumb, and you can buy even these systems, which this is even old technology, which is the size of a quarter, which has, I think this one has 9 gigs on it. So I mean, like memory, computation is all getting small. The power requirements are getting smaller. So it's really cool. So that's not a limitation for this. We're there. Communications, again, on the surface, there's no problem to get 1 kilometer communications to be able to set up these local area networks. Down in the caves, you'd have to literally time their directions of travel so that you did leave behind microbots, because down in caves, your communications are limited probably to 10 meters, 30, 40 feet between elements. So so 6.5 kilometers on the surface is what you can do, and 1 to 5 gigahertz. This may be a little bit thing, but you need very high frequencies. In a cave, you can communicate in caves with very, very low frequencies. They will penetrate the rock. The problem is that the antenna must be very long, tens of meters long, and that's not compatible with this design concept. So we go to very high frequencies, which are very small. 5 centimeters would be the antenna that we'd be looking at, but then we'd have to go to the local area networks. Okay, we actually did some studies for NASA, and we are still working on this for NASA for some reference missions. So, you know, some of the things we could do is we could explore 50 square miles in 30 Martian days, called the Soul. Okay, we could go down into a cave 5 kilometers in 5 days, and you could go. 1 kilometer. You go into a kilometer in 5 days with a small team of robots, and you could explore very large areas. So it would be pretty exciting to do that. That we've seen already, and we've seen that already. This is a reference mission. So that reference mission of 50 square miles would require 100 microbots at 1.5 meters, and they would do over 4,000 jumps, 6 jumps an hour. So they're moving relatively slow, and they do that in 30 days. And you've seen this video. I'm not going to play it much longer. Again, the mission might have multiple teams starting in different places. So the cave mobility studies, we actually have used some representative caves from here on Earth, because we do believe that the lava tube caves on Mars will be very, very similar to them, and finding out how they are. This is a communications video. I can play it. It's sort of just an animation of the way the communications would be bouncing from one to the other. 20 meters a line of sight between balls. That's 60 feet is what you could do based on our measurements. And 50 microbots would get in and meet the requirements of the reference mission, sending signals back up to the lander that would send them back up to an orbiter. What happened? Oh. It's doing its own thing. Oh, these are the balls going into the cave. Yes, they can hop uphill. They do better uphill in softer soils than in hard rock, but they will do fine in hard rock. So we show them uphill, going uphill, but these are just an conceptual animation of it.
Why wouldn't they just roll down?
Well, because they are centered, okay, so they'll eventually settle down. But because of the fact they have a foot on them, and the foot will have some ability to grab onto the rock, it would be very, very hard rock. In soft soil, they won't roll that far down. Yeah.
Can you string them together to make them into a net-like affair?
You could, mechanically attach them with things.
Yeah.
We haven't seen a real reason why you want to do that. There's some disadvantages of doing that one can come to mind, of particularly in caves of entanglement over surface features. You lose one, you lose them all, kind of thing.